Hey, I'm David. I'm one of the lecturers at the Maths Learning Centre at the University of Adelaide, and this is a lecture about integration, and I'll be solving just a few problems that use integrals. Just sharpen my pencil. Okay, so there were two videos before this. There's one about what an integral is, and there was one about the techniques for solving integral problems, like for finding indefinite integrals. And I'm going to join some of that stuff together to solve some specific problems using integration. So the first two problems I'm going to do concern areas because integrals are able to solve, able to represent areas, and the other problem I'm going to do is going to involve something else entirely. So it's going to be functions that are already the derivative of something. Okay. So I'm just going to do some examples. So this example, part one, is going to be find the integral from -3, -4 to -1 of 4x plus 8 over x squared dx. And number two is going to be find the area between y equals 4x plus 8 over x squared and the x-axis on the interval -1 to -4. Okay, so at first glance you might think these are the same thing, but they're not. Integrals are able to represent areas, but areas are not quite the same thing as integrals. If you look at the other videos, this integral means sort of like a weighted sum of the values of this function for every number between -4 and -1. And so the values of that function are allowed to be negative, and so any negative numbers that are in that zone will make the weighted total lower. But on the other hand, any negative places where the function is negative in that zone are not going to make the area lower because areas as drawn on the page are positive. So these two answers are going to be different to each other. That's the first thing to notice. So firstly, I'm just going to do the integral. So let's see. I'm going to need to figure out a function whose derivative is this. And even though it's a definite integral, I can imagine that those numbers weren't there for a bit, and I can do the techniques that I use for indefinite integrals. The first thing on my list of things to do is to just do it, and it's not something that I recognize. And the next thing is to rewrite it in some form. It looks like I can divide by the x squared, and that's going to turn it into something that can all be written as powers of x, so I'll do that. If I want to write an equals here, I'm going to have to keep these numbers here. I can't just pretend it's equal to that and figure it out. So I could rewrite it without those and figure out an answer, but I don't really need to. I can just keep the numbers there. So that's going to be 4 on x, because I can divide both top and bottom of that by x. And that's going to be 8x to the -2. Okay. And that integral I can do. 1 on x would become ln x. But it's 4 lots of 1 on x, so it's going to be 4 ln x. The 8's still going to be there. I have to put the power up by 1, so it goes up to minus 1, and divide by the new power. And I don't need a plus c when I'm doing definite integrals, because I only have to find one answer to this problem. I only need to find one of the antiderivatives, so I don't need the plus c, because the point of the plus c is to find all of the antiderivatives. And this means that I have to sub minus 1 into this and minus 4 and subtract. So the top number goes in, the bottom number goes in, and I subtract those two is 2 answers. So 4 ln absolute value of minus 1 plus 8. Oh, I guess that's going to become a minus 8. Look, I'm just going to keep it to make it as simple as possible before I sub anything in. 8 on x, I guess. Okay, so I sub in the minus 1 and the 4, and I subtract. So sub in the minus 1, 4 ln minus the absolute value of minus 1, minus 8 over minus 1, and 4 ln the absolute value of minus 4, minus 8 over minus 4. Okay, well the absolute value of minus 1 is 1, so that's 4 ln 1. And minus 8 divided by minus 1 is plus 8. And that's the absolute value of minus 4 is 4. Minus 8 divided by minus 4 is plus 2. ln 1 is 0. So I've got 8 minus 4 ln 4 minus 2. So 6 minus 4 ln 4. And just for my own sake, I would really like to know how big that number is. So I'm just going to ask a computer what that is. 6 minus 4 ln of 4 is 0.4548. Okay, so that's what that integral works out to be. So when I look at all the numbers that integral produces, and I average them out across the distance that it's going along, I get 0.4548. So the average value of this is going to be 0.4548 divided by this distance, which is 3. Okay. So number 2 is find the area between that and the x-axis. Now I know that the integral is going to be the area except that areas below the x-axis count as negative. So the only way I'm going to actually be able to find the total area between this and the x-axis is to figure out where it's positive and where it's negative. And I should really draw a quick rough graph of it in order to figure it out. So let's see. I'm just going to give the function a name so it's easier to talk about. Okay, so f of minus 1 is 4 times minus 1 plus 8 over minus 1 squared. So 8 minus 4 is 2, which is 2. And f of minus 4 is 4 times minus 4 plus 8 over minus 4 squared. Now 4 times minus 4 is minus 16. 8 minus 16 is minus 8. Minus 4 squared is plus 16, and so we get minus a half. So it crosses over, definitely crosses over between 2 and minus a half. I should just check that it doesn't have some sort of wicked discontinuity in this zone, which I should have checked before I did the derivative. This isn't defined when x is 0, which is going to be a problem when I do the integral, but x equals 0 is not in this zone, so that's all right. Okay. So since the function is defined for everything on this interval, and it goes from positive to negative, it must cross the x-axis. Even if it didn't go from positive to negative, it might still cross the x-axis because it might go down and then come back up again. So just be careful with that. Okay, so we should figure out where it crosses the x-axis. The x-intercept will happen when this is 0. And x isn't 0, so I can multiply by x squared. And the 4x would have to be minus 8, therefore, and the x would therefore be minus 2. Okay? So my graph is doing something like this. Don't really need all of that stuff over there because I'm only interested in a negative part of this story. So minus 1, minus 2, minus 3, minus 4. So at minus 1 the answer is 2. And at minus 4 the answer is minus a half. And it crosses at minus 2. Something like that. And this area, as drawn on the page, that is the area I am looking for. So what I'm going to do is I'm going to label areas as shown in the graph. I'm going to call them area 1 and area 2 in the graph. So this here shall be area 2 and this here shall be area 1. Okay. So these areas should be integrals, only this, if I do this integral, it will come out to be negative. And this integral should come out to be positive. So let's see. The integral of f of x dx from minus 4 to minus 2 is the integral from minus 4 to minus 2 of 4x plus 8 over x squared dx. And we already know what that works out to be. It works out to be 4 ln x plus, no, minus 8 over x, 4 ln of the absolute value of x, minus 8 over x from minus 4 to minus 2. And so we get 4 ln minus 4, no, the top one first. Four ln of minus 2 minus 8 over minus 2, 4 ln of minus 4 minus 8 over minus 4, which is 4 ln 2 plus 4 minus 4 ln 4 plus 2. So the 4 minus 2 is 2. Okay, well that's what that works out to be. Good-o. And that's going to be a negative number, okay? In fact, this subtraction here, I know that when the 4 can come out, I'll now get 4 ln of 2 divided by 4 plus 2. Which is 4 ln of a half plus 2 if I want. And I know that any number less than 1 ln will produce a negative number. And actually, half is 2 to the power of negative 1, and negative numbers can come out of things. It wasn't really necessary to do all of that, but I just wanted to check. And this is a negative number, and I know it's a negative number because on the graph it's going to be a negative area. It's below the x-axis, but just to check, ln2 is about 0.7. 4 times that is 2.8, and 2 minus 2.8 is a negative number. So I'm just going to approximately equal to 2 minus 4 ln2 is minus 0.77. 2, 6. Okay, so that's first integral. Okay, and so area number 1 must be minus that, because this is negative. Okay, now the integral from minus 2 to minus 1 of f of x dx is the integral from minus 2 to minus 1 of 4x plus 8 over x squared dx. And we know what that works out to be. It's 4 ln absolute value of x minus 8 on x from minus 2 to minus 1. And so we get the thing with minus 1 and the thing with minus 2. 4 ln absolute value of minus 1 minus 8 over minus 1. 4 ln absolute value of minus 2 minus 8 over minus 2. Didn't give myself enough space, did I? And so ln, that's 4 ln 1 plus 8 minus 4 ln 2 plus 4. And so I get 4 ln 1 is 0, 8 minus 4 is 4, and that's 4 ln 2. Okay. And let's just check. This should come out positive if we've done this correctly. So we have 4 minus 4 ln 2, which is about, which is about 1.2274. Okay, and so therefore area 2 should be 4 minus 4 ln 2, which is approximately equal to 1.2274. And just to check that we've got this right, area 2, which is the positive area, plus the negative area over there should be the total area that I had before. So just let me check this. 1.2274 minus 0.7726 is 0.4548, which is the answer we got before. Okay, cool. It's working correctly. Beautiful. So the total area between f of x and the x-axis on this interval is a1 plus a2, which is 4 ln 2 minus 2 plus 4 minus 4 ln 2, which amazingly is 6. And that surprises me completely. I'm just going to get a computer to do this for me. This is Desmos, the integral from minus 4 to minus 1 of, what was it? 4x plus 8 divided by x squared dx. That's the integral. Okay. And so if I do it from minus 4 to minus 2, I get that. And then I need to do it from minus 2 to minus 1. So that's the answer we got before. I'm going to have to turn this into, this is already a negative number. If I want it to be positive, if I do minus a negative, I get that. And, that's not at all what I was expecting. Minus 2, can't be minus 2. Let me do the absolute value of this then. It's this one that's the negative number. I get a 2. No. Look. Minus 2 plus 4 is not 6, it's 2. Right, okay. Kind of cool that it came out to a whole number. Not at all what I was expecting. Okay, so it's quite a lot bigger than the answer I got for the integral. Okay, and that's because so many of them are negative, as I can see in the graph. It might not go down very low, but there's a lot of it. Okay, so that's finding both integrals and areas. And if I want to do areas, I'm going to have to do my integrals as find the bit that's negative and find the bit that's positive and do them separately. Let me show you a little bit about how my working went. You'll see that I just had equals, and approximately equal to. I know a person who has experience with maths, when they're reading this, seeing all these lined up equal signs, it'll tell them that I've been calculating the same thing every time and I haven't changed what I'm doing. So in this one, I've done a little bit of reasoning here. I've told the person what I'm doing. The x-intercept is when that. So that means it's at minus 2. And I've drawn a diagram. And I've told the reader the important piece of information about the diagram. I've told them what these letters A1 and A2 are. And then I've calculated the integral. And it's all just equals. That's great. And then I've told them what A1 is. So I didn't say another equals here, because A1 isn't the same thing as this integral. And I calculated this integral. And then I said what A2 was equal to. So you'll notice that in mathematical working, if there's a whole string of equals, I know that's all just still calculating this thing. And the moment it says something something different to what it said before, that's when I know I've switched over to writing down something else. So it's important to not repeat the thing that you're calculating while you're still calculating the same thing, and then start something new by telling the reader what it is that I'm calculating. Okay, so just some notes on writing working there that might be useful if you have to hand in assignments and other people have to read what you're doing. Okay. So, okay, so now I want to do another problem that involves areas. Actually, I'll do yet another one. What is the average value of f of x, which is going to be equal to It's going to be equal to x x plus 2 cubed. Yep. On the interval from, let's say it goes from, I'll do 0, from 0 to 5. Just a random thing. So this function, the idea is it has all these different function values. It ranges from 0 when x is 0. No, I'll go from 1 to 5. It ranges from 1 times 1 plus 2 cubed, 27, up to 5 times whatever 7 cubed is, which is gigantic on that zone. Doesn't have any negative numbers in that zone, but there's nothing stopping it being negative. There's going to be a small zone between sort of x equals 0 and x equals minus 2 where it's negative, but that's neither here nor there. Okay, so I've had some thoughts about what this function is like. I could attempt to graph it actually, if I wanted, but it doesn't make a difference to the average value. But I will draw a graph. So here's 1, 2, 3, 4, 5. When I put in 5, f of 5 is 5 times 5 plus 2 cubed, which is a horrifyingly huge number. 5 times 7 cubed is 1715. Okay, it's huge. And f of 1 is 1 times 1 plus 2 cubed, which is 1 plus 3 cubed, which is 27, which is going to be like way down here compared to the 1700 up there. And I'm guessing that it's just going to be a curve like that. There's a place where it meets the x-axis over here at minus 2 actually, and I reckon it's going to go down here like this and then like that, because it looks like an x cubed at this spot. There should be an inflection point there, but none of that's necessary to actually do the thing. And I want to know, what is the average of all these values? And the average value, the whole point of the integral is it's the part of an average, when you calculate an average and you add up the total of everything, the part of the average where you add up the total, that's the integral. So the average value is the integral from 1 to 5 of f of x dx divided by the width from here to here, which is 4. Okay. Now, the integral from 1 to 5 of f of x dx is the integral from 1 to 5 of x plus 2 cubed dx. I could expand it out. A substitution might help. So let's see. I've got two choices. I could do integration by parts, or I could do a substitution. I'm going to show you the substitution, if that's all right. Let u be x plus 2, and then du on dx is 1, and so du is the same as dx. Okay, that's easy. I've dealt with the dx, and I've dealt with the x plus 2. I'm going to have to deal with this x. And also, u is x plus 2, and so u minus 2 is x. All right, well, what that's going to do is that's going to call this thing inside the x cubed u, and this thing outside the x u minus 2, and it's going to be easier to expand out. And so, therefore, the integral from 1 to 5 of f of x dx, it's close enough to have this to be able to see what's going on. Wait. This 1 is referring to the value of x at this spot, and this 5 is referring to the value of x at this spot. So I'm going to have to figure out what they are in terms of u. When x equals 1, that implies that u has to be 1 plus 2, which is 3. And when x is equal to 5, that implies that u has to be 5 plus 2, which is 7. Okay, cool. So the x equals 1, and I am going to repeat it just to be sure I know what's going on. Okay, when x equals 1, that means that u equals 3. When x equals 5, that means that u equals 7. The x is u minus 2. The x plus 2 is u. The dx is du. And so now everything's in terms of u. I can just calculate it. And it looks like expanding it out might be the go. U times u squared, u cubed is u to the 4, minus 2u cubed du. Beautiful. power goes up by 1 divided by a new power. The minus 2 is multiplied on, so it's still there. Power goes up by 1 divided by a new power. And that goes from u equals 3 to u equals 7. So I probably don't need the equalses here anymore, because now that everything's in terms of u, we know what the variable is. Okay, so we have to do what it is when we have 7. A fifth is 7 to the 5 minus 1/5 of u to the 5 minus a half of u to the 4. Okay. So that's going to be 1/5 of 7 to the 5 minus a half of 7 to the 4 minus 1/5 of 3 to the 5 minus a half of 3 to the 4. Wow, that's a shockingly huge number, whatever that is. I guess there's a 7 to the power of 4 in both of these pieces. Wow, okay, big number. I'm just going to ask my calculator to calculate all of that at once. So 1/5 of 7 to the power of 5 minus a half of 7 to the power of 4 minus 1/5 of 3 to the power of 5 minus 1/2 of 3 to the power of 4, 2152.8. 2152.8, exactly. I should probably tell people it's exactly if I use a decimal, because most mathematicians assume that when you use a decimal, it's not the exact answer. Okay. And so the what were we calculating here? We were calculating what this integral here was, and that integral in this is in this bit. So I need to sub that back in. So therefore the average value is 2152.8 over 4, which is 538.2 exactly. Okay. So most of the time, this number is very large. And it must be pretty straight for the average value to be about halfway between here and here. It's a little bit closer to the bottom, so it must have more values where it's lower than values where it's higher, so it must sort of go up like that. Okay, so that's the average value. It's not pretty edifying, we're just pointing out how to do it. And some thoughts about the way I've written this. I've set up what the average value is, and then I pulled out that bit and calculated what that was. And since I set up my integral, I had to restate the thing that I was calculating and then figure that out. And I can't just say equals, because the person reading it will assume that means it's equal to the thing directly above it. I'm calculating the average value, so I need to tell the person that that's what I'm calculating. Always when you're writing, especially if you're writing problem solving, tell people what it is you are doing so that they can follow it. Okay. Okay. Let me just think about this. Okay. All right. So we're going to consider the curve with equation f of x is 2x squared minus 3x. Okay. Secant from the origin to a point A, I'll call the point B, on the curve, okay, with the x-coordinate of B being positive. What should the x-coordinate of B be? For the area between the secant and the curve to be 9 units squared. Okay, big question, a lot going on. A secant is a straight line drawn from one point on a curve to another. And the area between them, well, let's see, it would only account for the parts inside the curve. So it would be useful to draw a picture of this. So let's see. This is a parabola. And it's a concave up parabola. So let's see. Sketch. The x-intercepts will happen when 2x squared minus 3x is 0. So x outside of 2x minus 3 is 0. So either x equals 0 or 2x minus 3 is 0. So x equals 3 on 2. Okay, so 1.5. And I know that the turning point happens halfway between those. So my sketch is going to be something like this. So there's 1, there's 2, there's 1.5. And therefore about there at 3/4. It's going to go like that. And I have a secant, which is drawn from the origin, well that's what this point here is, that's the origin, to some point on here, like that, and it moves around here as the point moves. And this is the point B. So the area between these two things should be this area below here, because this is the line, and the curve is below it, and so it should be this area here. Okay, so that's what we've got. Now, well, the only thing that I know about areas at the moment is that the area between the x-axis and something is represented by the integral. But there's this weird ass bit here that's going on. Okay, but I guess the area between two things, if I sort of smudged this all up, if I calculated how far apart they were, then the average distance apart times the width should be the area as well. So now you know that the area between two curves is the top curve minus the bottom curve. So I'm actually going to write that down. The area between is the integral of the distance between them. On the zone that they are. So there should be some number here, I don't know what it is, and some number here. So that's just sort of what I'm thinking. I just need to be more precise about that. Now, this earliest point is 0. This point, I need to know what that is. So I guess that's whatever the coordinates of B are. So I should give the coordinates of B a name. Let B have x coordinate B. And then the y coordinate, since B is on this curve, the y coordinate should be given by that function. The y coordinate of B is f of B, which is 2b squared minus 3b. Okay, cool. That's great. Okay. So I guess I could add that to my picture if I wanted. B 2b squared minus 3b. I know it's sort of jumping the gun to put it in now. So B is a point B, 2b squared minus 3b. Which has been added to the graph. Okay. All right. So this part I put in the cloud here is not actually something that I would draw on the page. It's just what I'm thinking. Okay. So that's great. So I need the distance between them, and the distance between them would be the top one minus the bottom one. So I'm going to need a formula for this graph, this line here. It has equation y equals mx for m, where m is the slope, right? I know it doesn't have a plus anything because it passes through the origin. So I guess I need to figure out the slope, but the slope should be the change in the y divided by the change in the x. And so since it passes through that point, the slope should be the y divided by the x. So slope m should be the change in y divided by change in x, which, since it goes through the point b, 2b squared minus 3b minus 0 for the origin, and b minus 0. So that should be 2b minus 3. So that is y equals 2b minus 3. Okay, that's great. Cool. So what does that mean? Okay, not 2b minus 3. M, the entire of m is 2b minus 3, 2b minus 3x. So the distance between the curves should be the top formula minus the bottom formula. And so the top formula is this one, the bottom formula is this one, and so I should now be able to find the area between the curves. The area between the secant and the curve is the integral from 0 at the left to b at the right of the top function, which is 2b minus 3x, minus the bottom function, which is the curve, which is 2x squared minus 3x. Okay, that square bracket is just a different shape of bracket so that I can tell where the differences are. So tell the difference between these brackets. So in my head, what I'm thinking is that this is the top function and this is the bottom graph. Okay. And so I can keep doing this working, I guess. Probably good to figure out what this is. 2b minus 3x minus 2x squared plus 3x, which would be 2b minus 3 plus 3x minus 2x squared, which would be 0 to b 2bx minus 2x squared. Okay, that's cool. And so I can do that integral. The 2b will still be there because the b is a constant. The x will go up to a power of 2. The x to the 1 will go up to x to the 2, and I'll divide by the new power. The 2 will still be there. That'll go up to 3, and I'll divide by the new power. It goes from 0 to b. So I'm going to have what it is for b and what it is for 0. So what it is for b is... I always get ahead of myself there. It's just actually easier to do a little bit of simplification first. So this is just bx squared minus 2/3 of x cubed. Okay, so I've got, that's what it is for b minus what it is for 0. So I've got b times b squared minus 2/3 times b cubed minus b times 0 squared minus 2/3 times 0 cubed. Beautiful. And so this is, these are both 0, that's nice. So I've got b cubed minus 2/3 of b cubed, just to be clear, minus 0. And b cubed minus 2/3 of b cubed is 1/3 of b cubed. So that's what the area between the secant and the curve is. So since equals 9, therefore 1/3 of b cubed is 9, which means that b cubed is 27, which means that b is 3. Fabulous. And so I've found it. So b has x coordinate 3. And just so that you can see how this works, this is the setup, and that's my line, and I've just done this integral, and if I'll just call this b. And as I change the value of b, change the value of b, this answer changes. And when I get up to 3, the answer is exactly 9. So that's me calculating this from the... Yeah, that's me using Desmos to try and figure it out. But what we can do is that we don't need a machine to do that. We can calculate all of that ourselves. So let me look back at the writing here. It was a good idea for us to have a quick idea of the sketch of the graph to see what was going on. And then we imagined that the distance, the area between things is the integral of the distance between them. And the distance between should be the formula for the top function minus the formula for the bottom function. And so in order for me to figure this out, I'm going to need to first figure out how far apart they are. I'm going to need to know what the x-coordinate is at this spot. So I gave it a name. And it was useful to give the x-coordinate for that a name because that was the thing I was trying to find. So if I can write everything in terms of that, I have a hope of setting up an equation and solving it for that. I could have here used m as my variable, but I didn't want to because then I'd find out what m was, and I don't actually care what m is. I only care what the x-coordinate of b is. And so look at the writing here. I have told the reader when I'm drawing my sketch, and I've also told the reader what the number b is. It's the x-coordinate of b. And I didn't just directly write this down either. I've deliberately told them how I figured this out. And then I needed the equation of both of these things. So the line has this equation, and I told them what the m stood for. And then I calculated what the m is so that I could get an equation for that. So there's a section here where I'm figuring out what the equation is. I set it up with an equation with an unknown, and then I have an equation with, well, the right kind of unknown. And then I calculated the area between the secant and the curve. But notice I didn't just start with equals, because for a start, this bit here wasn't actually written on my page. It was just in my head. So nobody knew that that's what I was doing yet. So I need to tell them that. Tell them that that's what I'm calculating. And so I kept calculating that. And I got all the way down to an answer. And then I told them what I was about to do. I told them that since that area is 9, I can set up this equation that tells me what b is. So I've been very clear about exactly what I'm doing and the reasons I'm doing it. Okay, one more example. But the key fact we've learned at the moment is the area between two graphs is the top one minus the bottom one. Okay. So the last example, or possibly two examples, is going to be things that that aren't really about areas at all. Because when I first defined integrals, I was very careful that the integral itself is an average value, and it's not an average value, but the integral itself is part of the process for finding an average value, and it's not technically an area. It's just that it happens to be representable using as an area if I want. But I also noted that there was one special thing that functions did, that functions and integrals did, which was that the area so far, or the running total so far, is a function of its own. So I'm just going to have a little interlude. F of x is a function that has an integral, that's integrable. Then this function I have to call this a different letter to that, or it's going to get confusing when I do the calculation. So if I do a definite integral from one place to another, then what this is, sort of, as I know, the weighted total so far. Okay, starting at A. But that's the idea there. So, here's the idea. If f of t already represents the changes in another function, represents how quickly a function is changing, then when you add up all of those little changes, it should give you the actual value of f. Should give you the change in f of x. Okay, so let me just say that again. If this function represents how quickly another function is changing, then you can say, oh, look at all these little teeny changes in that function. If I add them all up, it should tell me how much the big function changes by. Okay? So what I'm saying is that, i.e., if f of x is already d big F on dx, then the integral from one place to another of this function should be the change in f. And I mean, that's exactly what the fundamental theorem of calculus says. It should be f of b minus f of a, right? Which is the change in f. And that's a lot of a roundabout thing to say, but basically that's the idea. If your function is already a derivative of something else, so instead of thinking of it as like magic, a function that magically appears and I don't know how it's related, and so my only way of thinking about an integral is as an average value. But if my function appeared because it was already the derivative of something else, then the integral of my derivative function changes in the big function. And I think that's super cool. And that means that the average of the derivative is the average slope, which is even cooler, because the average slope should be the average rate of change, we know, is the change in f over change in x, right? But it's also the average value of df on dx should be the integral of df on dx. The integral of the function f dash x dx from a to b over the change in x over b minus a. And so this change in x is the b minus a, and the change in f is that thing there. So way back when we calculated average rates of change, we were finding literally the average value of the rate of change, which means we were doing the integral of a derivative, which is just thrilling awesome, I think. That might not appeal to you. I think it's fabulous. But the upshot of it all is that if you have something that you know how the derivative behaves of something, then you have a chance of figuring out how the original function behaves. So let me just do an example. So, for example, population of rats grew in a way that meant, let's call it P. Population of P of rats grew in a way that meant the rate of change of P was no, ignore that, sorry. fell towards an object in space fell towards the Earth. With its velocity increasing, getting faster and faster as it got towards the Earth over time. Velocity v increasing. Increasing with time. So that the rate of change of this was 2t. Let's see, we've got that. And this isn't particularly realistic. If you're doing real physics, there'd be a wickedly different number in that spot. No, that's fine. So the speed at which it increases, not just the velocity increasing with time, but the rate of change of the velocity increases with time as well. Okay. So the question is, what is the velocity at any given time? So at t equals 5, where t is in seconds, and v is in meters per second. Okay. T equals 5 seconds after we started watching it. The v was equal to, 100 meters per second. A. Find a formula for v as a function of t. And B. Find v when t is 20 seconds. Okay. That's the sort of example that you might be given. So let's see. We have a function and we know what that its velocity is changing, and not even that, its rate of change of velocity is changing. It's different for different times. And so we could do the integral, because we know that an integral is able to figure out a change in velocity, a change in the function that's a derivative. Okay? So A, find a formula for B for a function of t. Now, I've got two ways of doing this. I could do it as if I was just thinking about the change in velocity. The change in velocity should be the integral times the change in time, if I wanted. So that's one way, and then I'll do the other way as well. One way is this, the change in velocity, like the average rate of change is the change in velocity over the change in time, which we can figure out, okay? But I also know that the average rate of change is the average value of the rate in change. Sorry, the average value of the rate of change, which is the integral from t equals 5 to 20 of dv on dt dt. Divided by the change in t. And so therefore, the change in v must be I don't have to write this working down. I can actually just write it this way if I want. It's just talking through the reasoning. Okay, so the change in v is this, and dv on dt is 2t. And so we do the integral. 2 will still be there. Power goes up by 1. I divide by the new power from 5 to 20. And so that's t squared from 5 to 20, which is 20 squared minus 5 squared, which is 400 minus 25, which is 375. So the change in v is 375. But of course, the v was at 5 seconds, the v was 100 meters per second. So the change in v, so the value of v at 20 seconds should be the original value of v, v at 5 seconds, plus the change in v, which was 100 plus 375, which is 475 meters per second. So that's one way of doing it. No, that's not what I wanted at all, was it? I wanted a formula. Pooh, I've done part B. All right. So one way of doing this is to do part B first, and that's how part B works. And if I want this at a specific value of time, then I'm going to have to do this with this 20 being something other than the specific value of time that I wanted. That's going to be a little harder to do at time t. Now this is going to be a bit confusing because I've got some little t's. I want this to be an unknown time, and I would call it little t, except that this is another time t. It's going to be a bit confusing to do this. Okay, so that makes it a bit harder, okay? But if all I want to do is figure out the change in time, totally this is quicker. All right, that's one way. And A is, well, the notation's going to be hard. The change in V is going to be from 5 to some unknown time, dv on dt times dt, which I need to put something in that spot. And some people would put a t in that spot, but that makes it a little harder. And so you would often say t at the point you really wanted, which is like t2 or something. At time t equals, say, t star, and this would work out to be t star 2t dt, which is t squared 5t star, which is t star minus 5 squared, which is t star minus 25. And so therefore V is going to be the initial V, which was 100 plus the change in V. So therefore at t star, t equals t star, V equals this. Which is t star plus 75. And so, t star squared. And so therefore, at time t, V must be t squared plus 75. And so it's a bit tortured. And what some people will do is they'll happily put a t in this space and that space, remembering that this t is a variable and this t is a fixed value of t, a fixed unknown value of t, and just being able to keep track of them. So that's a bit hard, but another way, which I think is easier, is to do this. So for A, I would do this. I would just write down that dv on dt is 2t. So I know that whatever function v is, its derivative is dv on dt, which means that v is one of the antiderivatives of this function. That's the other way of thinking about it. So v is of dv on dt. And all of the antiderivatives of dv on dt, that's what an indefinite integral is. So I can do dv on dt. So therefore, v is the integral of 2d dt. Now, it's not technically equal, it's just one of those, but we're being a bit sloppy. This represents all of them, but there's only one that it actually is. And so I'll have 2 times a half of t squared plus c, which is how it's t squared plus c, and that's great. But I don't know which one it is. I don't know what the value of c is. There's going to be a value of c that makes this the correct answer. And I can sub in a value of t and a value of v to figure it out. So v equals t squared plus c for some c. Now, when t equals 5, v equals 100. So we have 100 equals 5 squared plus c. And so 75 must be c, and so therefore v must be t squared plus 75. Now I find this a much easier working to follow. It's a very useful thing to write this thing down, just to remind yourself what's going on. And this is using the idea that the indefinite integral allows you to find antiderivatives, whereas this one is using the idea that the average rate of change is the integral of the rate of change divided by the change in time. So you use whichever one makes most sense to you. This one makes the most sense to me. And so now when I do B, when t equals, I'm just going to write down the whole formula again. V is equal to t squared plus 75. So when t is equal to 20, v is 20 squared plus 75, which is 400 plus 75, which is 475 meters per second. And so I find this version of the working much easier to follow than the other, but some people feel the other way around. Okay. Thanks for listening.